Swayam Prabha. Digital India. Educated India.
For example, the same translating frame. So same translating frames. So we have fixed frame, we have another frame which is moving, okay, translating with respect to this one. So an observer which is there in the x prime y prime frame, so he sees this having a certain velocity, for example, okay, but so he doesn't know that he himself is moving with a certain velocity, so he is missing. So with respect to another frame, say the fixed frame, so a velocity of this frame has to be added to his observation so that the total velocity can be found out from this one. So this is, I hope in a simple way, this is what it is. While the rotating frame is a little bit more complex. So your doubt is if it can be understood with respect to the translating frames, so the same thing can be done with rotating frames also. So what we are saying here is that an observer sitting in the primed coordinates where he is moving, he doesn't know that he is moving. So he observes that a particle is moving with a certain velocity, okay, with his own reference. But however, with respect to another frame, say the fixed frame, so if you want to find out the time derivative of that with respect to this one, so we also have to add the velocity of the origin here, okay, of O prime. So that is why this happens in many things. The one which we are discussing at this moment is about the rotating frame, which is a little bit more complex, but at the same time, if you understand, so this is all because here, this is, so if you take the time derivative here, dr by dt, so here r is, total r is xi plus yj, and r prime has its own coordinates, and this one r prime is prime. So these are, I hope you can understand that various values of x and y, and these ij's are, and I prime j primes are very important. So these are the reference directions. So for example, any observation is made not only with respect to the origin, but the directions with which it is doing. For example, if you are saying that you are going at 30 degrees angle at a speed of say 40 kilometers per hour. So what is that 30 degrees? So 30 degrees is with respect to the north, or maybe with respect to the east, okay, north of east or south of east, so something like that. So unless the directions are prescribed, I and j or I prime and j prime, so they have no meaning. Of course, the origin is also very important, but the directions are also very important. So in this particular translating frame relationship, so the directions of the frames are same. For example, here I prime j prime is the same as ij, right? They are always pointing in the same direction. And so if you go for the time derivatives, so that means that dr by dt here is, so you take the time derivatives in every frame. So this is how it is. So here, all these time derivatives are only the time derivatives are coming because of xy, while ij and I prime j prime are exactly same. So I prime j prime is the same as ij. So they can be replaced by ij. So essentially, this is what happens here, right? So the velocity as observed in xy frame, small xy, is the same as the velocity of O prime I hope this is in terms of velocities. So the total velocity of the point P with respect to the XY frame, I think I'll slowly switch to this big XY and small XY instead of putting primes all the time. So this is the one, this is the observation made in the moving frame. To that, we have to add the velocity of the origin of that, because as I keep saying, so anything that has to be given as a vector, okay, the position of any point is with respect to an origin and with respect to a certain directions. So these two, without those two, you cannot say anything about the moment of anything. Okay, so I hope, so these things are very important. Whatever you raised is a genuine doubt. Everybody should be clear. The other one which we were talking as the last class is about the rotating frame part. Is about, this is what we are doing. This is what, so there's a point P here. I did this. This is, I'm just for the sake of recapitulating, I'm just doing it because it's a very important one. And this P is observed in both observed in XY, that's a fixed frame. So you call it as R. And P is also observed in prime by prime, which again you may call it as R prime or R itself. Okay. So this is what, so we have, so what we are saying here, interestingly, so this is what we have to appreciate. So this is what you have to appreciate. So either you call this R observed in the XY fixed frame, in which case we take this and this as the two quantities, X and Y, and X multiplied by I is this direction and J is this direction, right? And it is the same as the X prime here and Y prime here, which are in the direction of I prime and J prime. Okay. So if you take the time derivatives, so what we do here is we are talking about this. So that means that we are taking Ij as fixed and I prime J prime as rotating with respect to Ij. So if you take the time derivative, so this is nothing but dr by dt. I'll just write it here. Okay. So as observed in XY, big XY. And here there are two parts which we have discussed in detail, is maybe I'll write here. So if you take the time derivative of this one, dx prime by dt, there are two components. And I'll also write, I'm writing it quickly because we have done this. So this is how we can write. So these two are the time derivative of the first term. So here what we are doing, please observe that we are taking Ij as the fixed frame and we are assuming that I prime J prime are having a rotation with respect to Ij. It can even be reversed also. It can even be with respect to something else also. But here we are assuming that the difference between the observations made in Ij, which we think is the absolute time derivatives, and how they are related to the observations made in the rotating frame. Okay. So since the rotating frame, so these X prime and Y prime, which are functions of time as such, while this I prime, J prime are also functions of time, okay, with respect to XY. Okay. So that means that these time derivatives as observed in the fixed frame are related to these two. So this is nothing but x prime dt. So this is nothing but x prime dot let's change it. And these things which we have seen, which we have derived in very detail. So I'll put it as theta dot. So theta is the angle between fixed frame and the rotating frame, and so x prime. This is the one step in between step, which there are so many primes, so many dots are coming. So please. So this can also be put as product of, as a cross product of okay. So this j can be put as k cross I, and this I can be put as minus this with minus, that becomes k cross j. And this is where you have to make attention carefully, is that the one thing which is in this bracket, so x prime is an observation made in the rotating frame, and you are taking a time derivative of it. So how much it is moving, okay, the time is the same. Time, whether you are doing either the fixed frame or rotating frame, so time clicking is same. So how you see this one? So this is x dot in the direction of I prime, y prime dot in the direction of I prime. So this is nothing but the relative velocity as observed. This is the velocity as observed in x prime y prime, while this is theta dot k times. So this is nothing but the position vector. So x prime I prime y prime j prime is nothing but the vector as measured in x prime y prime. In fact, this is the same. This is the same because it is, this vector is in this direction, whether you talk about the moving frame or fixed frame. So but however, we say that this is r x prime y prime. So this is what, so this is interestingly, so this is the relationship which says that, I will explain this one just now, is that the velocity in the fixed frame supposed to be, which is the absolute velocity, is nothing but velocity as observed in the rotating frame plus a rotational component which is coming. So theta dot k, if you want, we can put it as omega by itself. Omega as a vector, you can know that. So theta dot k I can replace by omega. So that omega is nothing but angular velocity vector of rotating frame. So theta dot k, we know the usual convention. So if it is going counterclockwise, we obviously, the angular velocity can be represented as a vector. So coming out of the board. Okay. So these are, let me explain this thing a little bit here. Why it is happening. Looks sometimes trivial, but sometimes you suddenly start having a lot of doubts. Let's assume that, as a simple example, so let's assume that there is a ant or maybe a bead moving along x prime y prime, along x prime. Let's assume that it's moving along this one. So okay, at this moment it is here. So if you think it is not moving, let's say that is the first example. So if you think it's just not moving, okay, it is stays fixed there at a distance of say some r along x prime. So and then the frame is rotating. So if you assume that the observer in the rotating frame, what will he see? He sees that the particle is at a constant position all the time without having any velocity. He sees no velocity. But you know very well that this frame itself is rotating, and obviously this this bead here, okay, thus seems to be staying fixed, so is actually rotating. So, right? It is having a linear velocity here at that instant, right? How much is that? So this is maybe omega r. So that's exactly what it is. So here, as that simple example, so here in the rotating frame, he will not see any velocity, but however, this is the rotational component, omega cross rxy. It is nothing but, if this is r and if this is omega, omega cross r is nothing but this velocity here, this term, omega cross rx. Okay. On the other hand, if you think that this point is moving with a certain velocity here, as far as the rotating frame is concerned, which we call as, let us say, we call it as x prime y prime. So this bead is moving along x prime axis with a certain velocity. So the observer here in the x prime y prime axis, so he sees that it is moving along x prime. So he doesn't know anything that he himself is rotating. Okay. So what he sees here is that, okay, at this instant, this is moving in this direction. But in reality, what it is that this also is rotating about the fixed frame. So you also have this one, which is r omega. So this, then the total velocity is this. This is the total velocity. So this is Vx prime y prime, okay, as observed in the rotating frame. And this is the second term there, which you call as a rotation component or even a correction term. So this is this, and vectorially you sum it up to get the total velocity here with respect to the fixed frame. Okay. So this is, I hope you can get a clear picture. What are the various components here? So this is the relative to the rotating frame. And this is the velocity, that is the second term, r omega, that is the rotational velocity component, and the total is here, this one. So in reality, the particle is moving along this direction with respect to xy axis. So I hope you can appreciate this part of it, because the next part, which I have already derived last time, is involves the time derivative of the next one. Okay. So probably it's a little bit of repetition. So we will do that. So what here, we'll write here. So this is what it is there, right? Or we can even write it one step before, is that dr by dt of fixed frame measurement. So this is dr r prime as seen in x prime y prime, and this is, so this is, both are same. This is the final result. This is a one step below that. Why I wrote this one is that here, this is r, we are taking it as a position vector, but it can be any vector. There can be many observations that can be made. Even the next step, the velocity, you want to see the time derivative of velocity, which is acceleration, or many other things. So any vector that's observed here. So rxy, this applies to the relation between vectors between time derivative of vectors as observed in two frames. This is the important part here. I said it is two frames. In fact, here we are talking this xy is a fixed frame while x prime y prime is a rotating frame. But it can be the other way. It can be both may be rotating, both may be moving. Okay, both may be moving. But if there's an observer here, for example, if this xy itself is rotating and with respect to x prime y prime is also rotating. Okay, so if you just want to relate so the observations, the time derivatives that's observed in both the frames, so then this is the relationship. Okay, so this can be done as, so we can generalize it to any a here. Okay, so this can be observed. So that means that here the time derivative as observed in the xy frame, well, I wrote it down here. So as observed in the x prime y prime, and then there is a rotation component. So this is a correction term if you call it. Okay, so why expressing it in this manner is that we can generalize, we can go for one more step for velocities. So this one, we want to go one more derivative. One more time derivative. To get acceleration relationship. Okay, so we have this velocity relationship, which we want to take one more time derivative so that we get relationship between accelerations as observed in xy frame and how they are related to x prime y prime observations. Okay, so to do that, so that means that we do, so on this side we have d dt of vxy. Okay, and we have d dt of vx prime y prime and d dt of, so we have done this, and so I just want to go through these steps again only because they are important. So this is what we want to do here, and so this is observation is made in the big xy frame, fixed frame. So this is nothing but, that means that this is nothing but acceleration in the xy frame, right? So while this is the one, here, this is the interesting part, the observation is made in the x prime y prime axis, and then we want to get the time derivative, okay, related to xy. So for that, we make use of this one. Okay, so if you want to get that relationship, then what we have here is that there are two parts here. This one is that d dt of okay, so the observation is made of velocity as well as the observation for the time derivative is also made in the rotating frame. Okay, how that observer makes it. So then this is the correction term. Okay, so that's that part. And the second part is that it has two terms. One is omega, so d omega by dt. So we will write it as alpha. And then omega cross d dt of okay. So, and then we'll continue this one, and that so this part I can just continue as the observation is made in the x prime y prime, as well as the time derivative is also observed in the x prime y prime, and that's called the acceleration. So then we have this, not going to do anything. Yeah, this is a continuation of that. So I'm just doing that, okay? And right, then the next term, alpha cross. And then we'll continue with this one. So interestingly, so this is an observation made in the rotating frame. So if you want to get the time derivative in the, change it to fixed frame. So we will write it as we'll again apply this, and then we have another. Okay, so I had to apply that repeatedly, and then finally and then we have, I'll just collect all these terms. You will see it. And we have one here and one here. Okay, so we have okay, so this is finally what we get. So there are, you should try to understand. I will simplify this further. So what he says is that this is the, if you want to get the total acceleration with respect to the fixed frame, so that will have several components. One is the acceleration as observed in the rotating frame. And then there are, then what is this alpha cross rxy? Anybody can tell? Alpha is the angular acceleration of d omega by dt. So d omega by dt as a vector, if omega is coming out of the board, and if it has a time derivative, so if it has an acceleration, angular acceleration, so that is alpha. Alpha k also will be in the same direction. K is constant. So similarly, we have another omega cross rxy. Can anybody tell what is, how you simplify this one? This is very interesting, and we should know how to do it. And then there is another term here, 2 omega cross v x prime y prime. So this takes, probably it will take a while for you to appreciate each of these terms. I'm going to simplify the terms. So for example, alpha cross, okay, so this is, interestingly, okay, let me, this seems to be a triple product, so let us just concentrate on this one first, then the other one will follow. So omega is what? Omega is omega k cross omega k cross. So this probably you should try to understand graphically. It's easy to understand. So what this is that so this is what is, if this is r x prime y prime OP, okay, And if you have omega k here, what is this term? So if omega k is coming out of the board, and then if you take a cross product with rx prime y prime, so you know that both are 90 degrees to each other. So the magnitude is omega times r itself, and the direction here is right. So if you take a cross product of omega with r, so you know that it's going to move in this direction. So this is omega k cross, right? So this is the one, right? This part. And magnitude is what? Magnitude is magnitude of this one is omega times r x prime y prime itself, right? Magnitude. And now we have another cross product, omega k again. So again, you have omega k here, which is coming out of the board. And then if you take a cross product with this one, the magnitude is obviously is the product of these two. And what is its direction then? So its direction you should be able to see. So if you rotate it like this one, so a right hand screw, so it will be moving in this direction. So this is omega cross rx. What is the magnitude of this one? The magnitude of this one is what? It is earlier this was omega rxy, so I have another omega, so that means it's omega squared r x prime y prime, right? So the magnitude is this much. So, and the direction is in the opposite direction of r x prime y prime. So in all together, very nicely we can put it. So if you, for this 2D problem, so the whole thing omega cross rxy can be related as omega square rxy with the magnitude, but it is in the opposite direction. So how can we represent it in both vectorially and as well as magnitude wise is minus omega square interestingly. So the whole thing can be put as minus omega square and with a minus of rxy. So that means that the total magnitude is omega square times the magnitude of this one. So rx prime y prime itself, and it is in the opposite direction of this vector. Okay. So this is a very easy simplification. Okay. And so this is, can you tell me what that looks like? I mean, you must have, you were exposed to many times. What is omega square r? Exactly. So it's a centripetal acceleration. So if there is a point P which is rotating in a circular motion, so omega square r directed to the center is nothing but your centripetal acceleration. So this is because the frame here, this is the frame which is rotating at omega. Okay. So obviously if there is a point P here, so it has a centripetal acceleration towards the center. So this is so this is the observation made here, but he is missing the centripetal acceleration because he doesn't know that he is rotating. Okay, so since he is rotating at an angular velocity of omega, so there is a centripetal acceleration directed to the center. So that is this part. What else is this? Can you tell me what this is? So alpha cross rx prime y prime. Why is this necessary? So this is also is because this observer doesn't know that he is rotating at an angular acceleration with an angular acceleration. So if the frame itself is having an angular acceleration of alpha, so alpha times r. So what is that? So alpha times r. So if somebody is here, so I will show all those things. So it is nothing but, what is that? Angular acceleration multiplied by the radial distance is nothing but the tangential acceleration, right? So this is the tangential acceleration component which he has missed, right? But only thing he sees is only this one. So this is the tangential acceleration component which is missing. This is the centripetal acceleration which is missing. And then there is also a 2 omega cross v x prime y prime. What is this one? This is not so clear, which probably most of you know it as Coriolis acceleration component. I will also explain why it has come. So let me try to show this again. First few times I'll come to the Coriolis acceleration also. What is this one? So the magnitude of this one is a cross product. It's the magnitude of this one is nothing but the omega times the velocity as observed in the rotating frame. So that is the magnitude, and its direction is how determined by the cross product of these two vectors. So for example here, so if the velocity of, let us say that there is let's try to explain it with respect to something here. Let's try to explain this with respect to, imagine that there is a board here and there is slot here. There's a slot here. Oh, okay. Sorry. Yeah, I'm trying to explain this one with respect to drawing a small situation. So where you have an x prime y prime frame which is at an angle of theta at this particular instant, and it's rotating with omega and alpha. And then what's happening is that a bead here is moving in the slot, a point P. So there's a slot. Obviously, slot is in the board, in the cardboard, or maybe a wooden board, in the x prime y prime fixed, and then the whole thing is rotating. So if this is rotating, so if this is, I can explain one term after the other here. For example, if this P is moving with a velocity, x prime, as well as an acceleration. So it is having a velocity v prime. Maybe I should have put v prime for simplicity. Vx prime y prime with respect to this frame, as well as there is an acceleration with respect to x prime y prime. So as far as this observer is concerned, so he thinks that the bead is moving, having a linear velocity and a linear acceleration along the slot. Okay, so he thinks that this is the only acceleration component. But what more is there? What more is there is the tangential acceleration. So how much is the R? This one is minus omega squared. So that means that if I show here, if I draw this one, this is R. And what is alpha cross Rxy? So this is alpha k cross Rxy. So if you have alpha k is like this, and if you take a cross product, okay, with this one like this one, so this is the one which is the tangential component, so which is alpha times R prime y prime. So this is this component. So let me call this as 1, 2, 3, and 4. So 1 is what? 1 is this one. So this is 1, and this one is 2. Okay. And what is 3? So 3 is omega cross rxy, which is nothing but minus omega square rxy. So that means that it is so this is 3, which is minus omega square or this part, right? And what is this one then? Finally, we are left with omega cross v x prime y prime. What is this fourth component? The fourth component is omega cross v x prime y prime. So we have v x prime y prime in this direction as acceleration, and then we have a omega here. And then if you have to take a cross product like this one with this one, its magnitude will be omega times v, and what is its direction determined by the cross product. So it will be like this. So this is the 2 omega v, and this is the fourth component. So I hope you got all the 4 components. So this is the one is the observation of x prime y prime, which will be in this direction as a acceleration component, and then this is the tangential component because of alpha, and then this one is because of the third component, which is the centripetal component, and then there is another component here, the fourth component, which we call as the Coriolis component, which needs a little bit of explanation. It is not so clear why it is coming. Why it is coming is not so clear. It's okay. So these 4 components, so you add up vectorially, and that will give you the acceleration that is observed in the xy frame, if you call it as a fixed frame. Okay. So that means that this is the observation made in the fixed frame. This is the observation made in the rotating frame. All other terms are the terms which we need to take into account because of the observation discrepancy. Okay. So we have a tangential, we have a centripetal, and we have a Coriolis. Okay. I will explain this one, why this is coming to, why there is also a 2 coming. Okay. So it is because a very interesting thing. Let's try to understand. We said that, okay, Coriolis component is 2 omega cross vx prime y prime. So sometimes this is called a relative term, relative to the rotating frame. Okay. So let's try to understand. So let us think that there is a rod here. There is a point P here. Okay. So what's happening? So let's assume that this is moving along this rod. Okay. It's moving along this rod. So let's try to understand what happens in a very small instant, delta t. So at this moment, it's moving along this one. But however, to start with, it has a velocity here because of the rotation, right? You have a rotating thing here. How much is that? Which we said it was missing because of the rotating frame. So this was nothing but your, how much is that? If this is R, and if you have a omega here, so this is R omega. So what's happening after that very small instant delta t? So after very small instant delta t, you are going to P prime. So this is a small distance. How much is that? So if you call this as delta R, is nothing but your velocity times delta t, right? So what's happening here? Interesting thing. So the point P has moved to P prime, and its radial distance has increased. So this is originally r, it became r plus r prime is r plus delta r. Okay, so the total distance has increased by a small delta r. What's happening here? Then the rotational velocity here, what happened to this one? So the rotational velocity here has become r plus delta r into omega. Interesting, right? So that means that in a small delta t time, the velocity, the tangential velocity has increased from r omega to r plus delta r omega. So if there is a change in the velocity, then obviously it gives rise to, acceleration. Right? It gives rise to an acceleration. So how much is the acceleration then? Change in the velocity. So this minus this. So it is delta r times, how much is that? Omega. And this has taken place in a time of delta t, right? So this delta r times omega is the increase in the velocity in a small time delta t, and so this is the delta r by delta t times omega. What is delta r by delta t? It is nothing but v, and this is omega. Okay, so that means that this is because there is an increase in velocity. What is its direction? Its direction is like this. So this one component of this Coriolis is in this direction, given by v omega. What is another v omega? Anybody can tell me? This is the most interesting part of, if you understand this, you would have understood how the whole kinematics takes place in the case of moving frames. Okay, this is because the particle is moving along the rod. There is also another thing that is taking place in this small delta t. What's happening? So the same thing I draw here separately. So here this bead is there, and it's having a velocity of, this is r and this is omega, and it's having a velocity of r omega. Okay, so now let's not assume that it is moving. Okay, now we assume that the so which is theta here has changed its by this rod has changed its orientation by an angle of delta theta. So what's happening here? Then because of this r omega, which was perpendicular to this one, has changed to r omega at a angle like this one. Okay, so what is that then? Okay, so can we find out what is the change in the, oh sorry, yeah, so because of two things, that I'm sorry, this is anyway not this one. Actually there's another thing which I should, because we are looking at the interaction of sliding velocity with omega. So I'm sorry, not this one. So we have a velocity here, and we continue to have the same velocity v prime x prime, right? So what happened to this one? So that means that a velocity which is originally like this has changed its direction by a delta theta in a small time. And what is the change in the velocity then? So the change in the velocity is, which is nothing but v times delta theta, right? So this is a delta theta, and this is given by V times delta theta. So this is the change in the velocity, and the acceleration component is nothing but V delta theta times delta t, and this is V omega. So this is the other component of your Coriolis. One is the first component, this r omega, the tangential velocity, which is missed, so is increasing by when the radial distance is changing to a higher value. That's number one. The other one is the velocity v. So since it is changing its direction by a delta theta, so that also gives rise to an acceleration component. So these are the two components which form the Coriolis components 2 omega cross v. Okay, we'll continue this tomorrow, and please go through this one. So Miriam has, any book has given enough in its own direction. Miriam also has given a lot, so please go through this one, because the next tutorial, as well as many things which are going to follow later, are based on this. Okay, I think I'll stop here.